So I'll be starting my session. So today we are going to the next section of our fifth module, the second part of fifth module, and that is task, process, and threads. Can you hear me? Can you hear me? Okay. So this section you had studied at an operating system, but we have to study a few of the scheduling algorithms in this section. And there are around 8 to 9 scheduling algorithms, but we have to study the first 4 in detail, and the others are just an overview. So let us start with this. So you might know what a process is and what a thread is, task is, etc. Because you might have come across these terms in most of the subjects you have studied earlier. So I'm just going through what a task is. So, when you define a task, it is a program in execution. Task is a program in execution, and the related information about the task is maintained by the operating system for that particular program. So the term task, job, as well as process, it refers to the same entity in operating system context. So most of the time we use these words interchangeably. So instead of task, we can use the term process, or instead of process, we use the term job, etc. So these terms can be used interchangeably in most of the cases by in the operating system context. So it is task is also a program in execution. Likewise, this process, I have stated these terms just to introduce to you that task is also a program in execution. So process, it is also a program in execution, and you might have studied an operating system. It is a program in execution. A process is a program or any part of it in execution, or it can be defined as an instance of a program. So a program is a huge piece of code out of which certain portions of it will be running at certain times. So that portion of the code which is currently active is called a process. Okay, so it can be an instance of a program. The entire program might run, or a certain at certain times, certain parts of the program might be in execution. So this program, whenever it executes, it turns out to be a process. So a program, when it is not in execution, we call it as a simple program. Whereas when the program starts its execution, we call it as a process. So a process is a program which has started its execution. Is it clear? Is it clear to you? Hello? So a process is a program which has started its execution. So once a program is starts its execution, we call it as a process. Okay. Is it clear to you? Hello? Okay. So now what is a thread? So threads are lightweight processes. In general, if someone asks what a thread is, then the general definition is a thread is a lightweight process. A lightweight process means a part of a program or a process that has started execution. It is a single execution flow of control, and that means it executes for a short while. It is a short piece of code that has been generated from a process, and it runs completely and stops. And so it doesn't, we don't have to say its process control block and all. So we call it as a process has its own process control block. So here when we come to thread, it does not have a process control block, and we call it as a lightweight process. So a process can have many threads of execution. Not a process, when it executes, it can generate many simple smaller tasks, or initiate many smaller tasks, and each of these tasks we call it as a thread. So we call a thread as a lightweight process. And threads can maintain their own states like CPU registers, its own program counter values, and stack. So these are the three definitions we come across in the next section, that is task, process, and threads. Anyway, task and process, the terms they are used interchangeably, and thread is the smallest part of a process, as a part of the process in execution. Now, we are going to the task scheduling models. You might have studied scheduling models in operating system. Likewise, in real-time operating system also, there are task scheduling models. If there are multiple tasks running in a system, then how the real-time operating system schedules all these tasks. And there are different task scheduling models. First one is the cooperative scheduling model. Second is the cooperative scheduling model with precedence constraints. Then third is the cyclic and round robin scheduling model with time slicing. Then fourth is the preemptive scheduling model. Mostly you might have heard of round robin scheduling model and preemptive scheduling model, also priority scheduling model in operating system. So all these concepts we come across here in RTOS also. Then the fifth one is scheduling using earliest deadline first. In embedded systems, most of the tasks must meet its deadline. So task can be scheduled based on the process which has to meet its deadline first. So scheduling using earliest deadline first or EDF precedence. Then another scheduling algorithm is rate monotonic scheduling model, or we call it as RMS model, which uses higher rate of event occurrences first. An event that occurs frequently is given highest priority. Then the seventh one is fixed or static real-time scheduling model. Then third is scheduling of periodic, sporadic, and aperiodic tasks. Then the ninth one is it's a general description like advanced scheduling algorithm which uses probabilistic timed Petri nets or multi-thread graphs, which are suitable for multi-processors and complex distributed systems. So this is not stated much in detail. We have to study the first four algorithms in detail and a definition of the other algorithms. Okay. Is it clear to you? So let us move on to the first scheduling algorithm. That is cooperative scheduling algorithm. So in cooperative scheduling, the name itself suggests that there is cooperation among the tasks that are going to be executed. That is, if one task is in execution, no other task will interfere with that task. Other tasks will wait for the running task to complete. Only when that particular task completes, the next task will start its execution. And once a task starts its execution, all other tasks waiting in a queue will wait until the task that is running comes to a completely executes. So that's why we call it as cooperative scheduling model. So here in this model, the scheduler switches the context between multiple ready tasks. There will be multiple ready tasks that are placed in a circular queue. So there will be multiple ready tasks that are placed in a circular queue. And the execution of these tasks from the queue happens in a sequential manner. That is one after the other. So in cooperative scheduling, there will be multiple ready tasks which are placed in a circular queue, and these tasks will be executed in a sequential manner. Is it clear? Is it clear to you? Okay. Now, the next paragraph defines what cooperative means. That is, cooperative means each ready task cooperates to let a running task finish its execution. And none of the tasks does a block. The task that has started its execution will not go to a blocked state anywhere during its execution from the start till the finish state. Once a task starts, it completes its execution without waiting for a IO operation or anything. Without that, there is no blocking state for each of these tasks. So the services in now the operating system runs these tasks based on the order in which these tasks are placed on the circular queue. If the task that has placed first in the queue will execute first, and each task is placed in the queue based on the interrupt that arrives. In RTOS, mostly tasks are initiated by interrupts. So whenever an interrupt arrives, corresponding to that particular interrupt, a task will be placed in the queue in the ready queue. And the one which has been placed first will execute first. And if it completes, once it completes, then the next task waiting in the queue will be executed. And the priority, thus from this we can understand that the priority of these tasks depends on its position in the queue. The one uh, that is in the front of the queue will be executed first and followed by the next one and so on. So the priority of tasks will be based on its position in the queue. Is it clear? Is it clear to you? Hello? Did you understand what cooperative scheduling is? Hello? Okay, Febina. You might have studied scheduling earlier, where we execute tasks based on its priority. Here in cooperative scheduling also, the tasks that are ready to execute will be placed into a circular queue. And these tasks are placed into the queue whenever an interrupt arrives, because in our course, tasks are initiated by interrupts. Whenever an interrupt arrives, the task corresponding to that interrupt will be placed in a circular queue. And the task that appears first in the queue will be executed first. Hence, we can say that the priority of the task depends on its position in the queue. Okay. Now this figure shows the program counter assignments or switching when the scheduler calls tasks one by one. So we can see that there is the first task. Can you see the figure? Okay. So the first task, T1, there is task T1 which executes first. And when task T1 I didn't say this figure, isn't it? I didn't explain this figure. So let us look at the diagrammatic representation of cooperative scheduling model. There is a main function that calls the operating system, and when there is a call to the OS will start executing each task one by one. Can you see the figure? There is a call to OS, and the OS will initiate each task. The scheduler program will run tasks one by one. Is it clear? Hello. Is it clear to you? Okay, can you see those arrows? Okay. 1 minute, please, 1 minute. Okay. So, can you see my mouse pointer? Is it visible to you, the mouse pointer? Hello? Okay, my mouse got stuck, I think so. So you just look at the figure. So can you see the arrow from call OS to the operating system? From the first block to the second block? Okay. From the second block, the arrow goes to the first task, task 1. Can you see that? The arrow to the first task. Task 1 is getting initiated, and when the task 1 completes, at the end there is an arrow pointing to the next task in the list of ready tasks. Isn't it? There is the star next written there for task 1, and star next means it is a pointer to the beginning of the next task, an address pointer to the beginning of the next task. And after task 1 has executed, the arrow points to the task 2, beginning of task 2. And now task 2 gets starts its execution. And when task 2 completes, it goes to the next task, and so on until the nth task has been completed. Okay. Once the nth task has been completed, again it comes back to task 1. This process continues. Okay, so from task 1, it goes to task 2 and so on till task n. And finally, when the task n has completed, it will return back to task 1. And that's why we call it as a circular queue. Is it clear? Is it clear to you? Any doubt? Okay, Ashwini. Thank you. Now, this task switching, that is from one task to other, how the program counter changes is shown in the next figure. When there is task switching occurring in the system, how the program counter changes. The program counter, it is a register that stores the starting address of a process or a program. So the figure below shows the program counter assignments or the context switching when the scheduler calls each task one by one in the circular queue. So you can see that task 1 will be executed first, and the shaded portion, it shows context switching. So initially, when the OS calls the task 1, there is a context switching occurring to task 1, and then the task 1 will execute. When task 1 executes, next there is a context switching to task 2. And after context switching, the task 2 will execute. And then it context switches to task 3 and so on till task n. Finally, when it reaches the task n, again it comes back to task 1. Okay, so it shows the different the changes in the program counter value. Is it clear? Hello? Okay. So now here we can compute the worst case latency, that is the time period spent in the circular queue. So worst case latency is the time period of the circular queue, and longer the queue, the greater will be the time spent to execute all the tasks in the queue. And that time spent to execute all the tasks is known as T total, T suffix total. It is the time taken to execute all the tasks in the ready queue. And it is the same for all tasks since all tasks are in the queue every time. So the T total is the same for all the tasks. And let us see how we can write a formula for this. For the ith task, suppose if there are n tasks and I'm considering one particular task, say ith task in general, then if DTI, D suffix TI, is the event detection time, that is the time at which the particular task has been brought into the list. DTI is the time at which the task has entered the list. STI is the task switching time. I said there is a switching time shown as shaded figure here. So there is a task switching time, and then there is a task execution time. ETI is the task execution time. So we are defining 3 different times associated with a task. One is DTI. DTI is the time at which a task has been brought into the ready queue. STI is the task switching time, and ETI is the task execution time. Now, if there are n tasks in the list, then for each task, all these 3 times will be there. And the sum of these 3 will give the total time taken for that particular task to execute. So the T worst can be defined as sum of all the tasks present in the queue. Sum of these times for all the tasks present in the queue. So we can write T worst as DTI plus STI plus ETI for the first task. I have written in brackets here 1 as suffix. Can you see that 1? DTI plus STI plus ETI, everything in brackets. It's the total time for the task 1. Can you see that 1 written as suffix? Okay. Then plus I'm going to add the time for the next task. All these 3 times are there for all the tasks. So we are just summing up all these times and writing naming it for the next task. So T2, suffix 2, etc. If there are n tasks, we have to write it for all the n minus 1 task plus n tasks. So, and all these time together will give us the T total. And plus, there is interrupt occurring frequently when the task is inserted into the queue. So, and total time for interrupt is also taken into account when T worst is considered. So, the total time for all the tasks in the queue plus the time taken for the interrupt service routine TISR is the time taken for the interrupt service routine to execute. And the entire time together with the interrupt service routine execution time is called T worst, the worst time for the task to execute. Or in general, we can write it as T total. T total is the time for executing all the tasks in the queue plus the time taken for executing the ISR. So T worst can be written as T total plus T ISR. And here TISR, as I said earlier, it is the sum of all the execution times for the ISR. If there are n tasks placed into the queue, there will be n ISRs that has been executed. And this T burst should be less than the deadline because embedded systems are often designed to meet deadlines. So the worst case, worst time should often be less than the deadline TD for any task in that list. Otherwise, the system cannot meet the deadline. So the T worst computed should be less than the deadline for any of the tasks in the list. So that is about cooperative scheduling model. And an example of this model is shown below, that is an automatic washing machine. And there are several tasks while the machine is in operation, but we are considering just 3 tasks, first 3 tasks. So the system can be partitioned into multiple tasks, but we are considering the first 3 tasks and naming it as A1, A2, and A3. And in a set of tasks A1 to AN, there are n tasks running in the initiated in the system when the system is in execution, but we are considered about only the first 3 tasks. And let us see what the first 3 tasks are. The first task is named A1, second task is named A2, and the third task is named as A3. So the first task is power on. We are switching on the power button. The user is switching on the power button. That is the first task. And the second task is water in. And the third task is water stop. These are the 3 tasks, initial tasks that we consider at present for this particular machine. So there are n tasks, but we are considering only 3 tasks. Now, when the first task runs, that is running the task 1, the scheduling, the cyclic scheduler by the kernel will perform its task by assigning the program counter the address of the first task. The program counter will be assigned the starting address of the first task, and then when it completes, the program counter is set to the address of the second task. And finally, the program counter goes to the third task when when task A2 completes. And so on, it goes up to the end of the task. And then finally, it comes back to the first task for the next operation, for starting the next operation, next cycle. Once the machine completes its execution, it will come back to the first step. And it will wait for the next power on to happen. Is it clear? Is it clear to you? Hello? Okay. So, and the third figure shows. So we were discussing the second figure, how the cyclic scheduler schedules the task. Then the third figure, it shows messages to the scheduler, because each task, when it executes or when it starts execution or when it ends execution, some message must be given to the next task to start its execution. So there are certain messages exchanged among these tasks. Let us see what are the messages exchanged. The message A1 is the start flag. this flag will be set when its function has been completed. That is when the power on has been completed. Then the message in A2 is the water stage 1 flag. Water stage 1 flag is set when the water has been completely filled. The water in operation is the task that is going on. When the water has reached the desired level, this flag will be set. And when this flag is set, it gives a message to the next task, message A3, and the task will start its execution. And in the task A3, there is a message. The message set is motor stage 1 flag. That is when water stops. Whenever the water stops, this message will be sent to the motor to start its execution, to start processing. Now, the context means where the address location is at. That is, the context of the first task is at address A1, the next context, the address A2, and the next third process, the context is at address A3. So these are the different states in which this task remains while it is in execution. So the 4 figures shows the different times and different states of the process. The first one shows that there are n tasks and the names of each task, what are the tasks running in the system. Then the second figure shows the scheduling of the order in which the tasks are scheduled. And third one shows the messages that are to be sent between the tasks. And the fourth one shows where the program counter is at during the execution of each task. Now the next section, the detailed explanation of each task is given. Hello, can you hear me? Do you understand what I'm saying? This is nothing but operation of a washing machine, and we are discussing each task one by one. So the first task I said, power on task, isn't it? The first task is power on, second is water in, third is water stop. We are considering only these tasks. I have put a dash after that, dotted lines after that, which means there are other processes following these 3 tasks. There are other tasks following these 3 tasks. We are just explaining about these 3 tasks. And it is called cooperative scheduling model. Why? Why we call this as a cooperative scheduling model? Because the water in will wait until power on task has been completed. Isn't it? The water in task will not start execution before task A1. It cannot start execution before A1. So it should wait for the task A1 to complete. Only when the power is on, the task A2 can start its execution. And that when the water is, only when water is let in, the third task water stop can function. So each task will wait for the other task to complete. Only then it will start execution. And this model is called cooperative scheduling model because each one of them is waiting for the other one to complete. So this is a typical example of cooperative scheduling model. Okay, so what task 1 is doing? That is, first task is power on task. So it has a waiting loop, and this waiting loop terminates after the detection of 2 events. One is when you close the door. And for a washing machine, you have to close the door and switch on the button. So when you close the door and when the power switch is pressed by the user, this waiting loop for the task A1 terminates. And it becomes ready to execute under the detection of these 2 events. That is, when the door is closed and the power switch is on, then it will start its execution. And it starts by sending a message to task A2. It will first send a message when everything is ready. When the power is switched on and door is closed, it will send a message to the next task A2 using a function, a semaphore function called OS_SEM_POST. That is, when a message is sent to the next task, the function called is OS_SEM_POST. When a message is received from the previous task, the function is OS_SEM_PEND, PEND, pending function. So these are the 2 functions that we come across in this section. One is to send a message to the next task, we use OS_SEM_POST function. And to receive a message, the function called as OSM pend function. So the function, the task that gives the OSM post, it will give the status of the flag for which it has been waiting for, and that is the start flag. The first task has been waiting for the task start flag to be set to 1. So the sempost function will be waiting for the start flag to set to 1. So when this start flag is set to 1, it is an indication for the task to execute. So task A1 sends a message to task A2 using the semaphore function OSM post of start flag. When start flag is set to 1 at the end of task A1, this message is sent to A2. Now task A2, it waits for message from task A1, because only when A1 completes, task A2 can start, and it is waiting for A1 to complete using a function called OSM pend function. So this pending function is waiting for the start flag to set to 1. So OSM pend function, it is waiting for the start flag to set to 1. When the start flag is set to 1, the water is let in, and when it reaches the adequate level, the water stage 1 flag is set. That is, when the adequate level is reached, it is an indication to stop the water. And so this flag will be set. Water stage 1 flag will be set. And this is a message which is sent to the next task from A2. The message A2, it will send this message to task A3 for execution. And A3 has been waiting using the semaphore function OSM post, and it was waiting for this water stage 1 flag to complete. So the third task was waiting for the second stage's flag to be set to 1. So the message OSM post water stage 1 flag, when it is set to 1, it is an indication for the third task to start its execution. And likewise, the task 3 waits for message from task A2 using the semaphore function OSM pend. So waiting is using the function OSM pend, and sending a message is using the function OSM post. So when a task is waiting for the previous task, it waits using the semaphore function OSM pend. And when it wants to send a message to the next task, it uses the function OSM post along with the flag for which it was waiting. So when task A3 completes its execution, the message will be sent to the next task, and it will post a message to the next task using the function OSM post, and the flag that is sent is motor stage 1 flag. So likewise, depending on the flag values, each task gets executed. So just remember, to send a message to the next task, the semaphore function used is OSM post, and when a task is waiting for the previous task to complete, it uses the semaphore function OSM pend. Okay, and along with the flag. Is it clear? Is it clear to you? Hello? Is it clear to you? Any doubts? Hello? Any doubts in this? Hello? Can you hear me? No response from any of you? Hello? Okay. Okay, thank you. So, hope you understood this. If you have any doubt while you're studying, just ask me, okay? So these are simple. You can just read through. You will understand what it is. We are just speaking about three tasks and how they are executing. These three tasks, they are executing one after the other. And when one task is waiting for the other task, we call it as cooperative scheduling model. And an example is shown here related to washing machine. Only three tasks have been considered. Now, the second task is cooperative scheduling with precedence constraints. Same cooperative scheduling model, but we are giving priority for the task. In the first case, we didn't assign any priority to the task. The tasks are given priority based on the order in which they are placed in the queue. But here, in this model, the second model also is cooperative scheduling, which means that each task waits for the previous task to complete its execution. But the thing is, instead of assigning priority based on the order in which it is placed in the queue, it is given the specific priority, and depending on the priority, the task is getting executed. So, I think it's time. Please say your attendance. Number 1, 2, 5. Number 5, answer. Absent.
Hassan Miss.
Okay. Answer.
Hassan Miss.
Okay, okay. Number 6. Number 7. 8. 9. 11. Number 11. Atul Dinesh is present. Atul Satyapal is present. Absent. Number 12. Number 13. Number 14. Number 14. Okay. Number 16. Okay, 17, 18, 20, 22, number 22. Okay, 23 Sarga, 24, 26, 27, 28, 28, 29, 30, 31, 32, 33, and number 3. Okay, absent Atul Satyapal, number 11 is absent today. Okay, thank you.